Hello students, welcome to Educate. We are going to continue with the chapter 11 of class 12 physics. So in previous lecture we have studied the basic concepts of photoelectric effect and Einstein's equation. Now we are going to continue with the same chapter. So we are starting with numerical. So here there is one example. Let's read it and then we will try to analyze. Monochromatic light of frequency 6 into 10 power 14 Hz is produced by a laser. The power emitted is 2 into 10 power minus 3 watt. What is the energy of photon in the light beam? How many photons per second on an average are emitted by the source? Right. So here you know very well that energy of a photon is given by E equal to h nu. We can put the value of h 6.63 into 10 power minus 34 joule second into nu. Frequency is given as 6 into 10 power 14 hertz. Now if we simplify, we will get 3.98 into 10 power minus 19 joule. So this is answer to first part. Now how many photon per second? So here it's obvious power is equal to total energy divided by time, right? So total energy, if there are n photons, then total energy will be n times E, and E is h nu, right? H nu we have evaluated. Power is given in our question 2.0 into 10 power minus 3. So we can write it here. We have to get value of n equal to P upon E. So P is given 2 into 10 power minus 3 divided by energy we have evaluated. So we have got 3.98 this value, which gives 5 into 10 power 15 photon per second. Now, there is another question. This question says the work function of cesium is 2.14 electron volt. Find the threshold frequency for cesium. The wavelength of the incident light of photon is brought to zero by stopping potential of this much. Here, stopping potential is given. It means we can find maximum kinetic energy, right? And then we can apply the Einstein's formula, and then we can get the related value. So here, first concern is to find out the threshold frequency. So here, this 50 is given. So 50 is 2.14 electron volt, and from formula 50 equal to, here nu 0 equal to 50 divided by h. H has value 6.63 into 10 power minus 34. If we simplify, here this is given in electron volt. So write the electronic charge here, value of 1 electron volt, that is 1.6 into 10 power minus 19 joule, and then divide. So after division you will get 5.16 into 10 power 14 hertz. Thus, for frequencies less than this frequency, no photoelectrons are emitted. As you have already studied that if frequency is less than the threshold frequency, then electrons will not be emitted because they will not have sufficient energy to come out. Now, next point is photo current reduces to zero when maximum kinetic energy of the emitted photoelectrons equal to the potential energy, that is EV0 by the retarding potential. So we can say EV0, this is total energy of incident radiation, minus this is work function. So hc upon lambda, you know, this nu is c upon lambda. So our concern is to get lambda. So lambda, this term we can shift to LHS. So EV0 plus phi 0, and which is equal to hc upon lambda, or lambda equal to that EV0 plus phi 0 divided by hc. So we can get this lambda equal to hc upon EV0 plus phi 0. Now we can put the values. So here h is 6.63 into 10 power minus 34 and c is 3 into 10 power 8 divided by EV0. EV0 we have evaluated, or in our question if it is given, it is given V0 is this electronic charge to be multiplied. So 0.60 EV time plus 2.14 EV, both are in EV, so we can take out EV common, and in place of EV we can write 1.6 into 10 power minus 19 joule. So we will get 454 into 10 power minus 9 meter, that is equal to 454 nanometer. So I think you have understood. Now wave nature of matter. So here we are going to see the wavelength and momentum. So, there a natural question lies, if radiation has a dual nature, might not the particle of nature like the electron protons also exhibit wave-like characters? So in 1924, the French physicist Louis Victor de Broglie pronounces the Broglie, this is not correct, put forward the bold hypothesis that moving particles of matter should display wave-like properties under suitable conditions. He reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. If radiation shows dual aspects, so should matter. The Broglie proposed that the wavelength lambda associated with a particle of momentum p is given by lambda equal to h upon p, and you know p is mv. So h upon mv, where m is the mass of the particle and v is its speed. So this equation is known as the Broglie relation. This is also pronounced as de Broglie relation, whatever pronunciation you give, because if you are a student of French, you will understand what is the correct pronunciation. Otherwise, you are free to say the Broglie relation, whatever. And the wavelength lambda of the matter wave is called the Broglie wavelength. Yeah, de Broglie wavelength. The dual aspect of matter is evident in the de Broglie relation. On the left hand side of the equation, lambda is attributed of a wave, while on the right side, the momentum p is typical attribute of particle. So this is mv, mass into velocity. So here particle nature, here lambda is wave nature. So, and h is Planck constant. Now equation, this above, for a material particle is basically a hypothesis whose validity can be tested only by experiment. However, it is interesting to see that it is satisfied also by the photon. For a photon, as we have seen, p equal to h nu upon c. Therefore, h upon p, we take this c upon nu, and c upon nu equal to lambda. So that is the Broglie wavelength of a photon given by equation this equals the wavelength of the electromagnetic radiation of which the photon is quantum of energy and momentum. Clearly, lambda is smaller for heavier particles, large mass m, more energetic particles nu. For example, so for more energetic particle, wave must be larger. For example, the de Broglie wavelength of a ball of mass 0.12 kg moving with the speed of this much is easily calculated. So let's see how. So calculation can be done. P equal to mv. Mass is given 0.12 kg and velocity is given 20 meter per second. So this will come out to be 2.40 kg meter per second. And lambda h upon p, we have calculated here, h we know 6.63 into 10 power minus 34 divided by 2.40 kg, so 2.76 into 10 power minus 34 meter. This wavelength is so small that it is beyond any measurement. This is the reason why macroscopic objects in our daily life do not show wave-like properties. On the other hand, in the subatomic domain, the wave character of particle is significant and measurable. What is the de Broglie wavelength associated with an electron moving with a speed of 5.4 into 10 power 6 meter per second? So for electron, we know mass equal to 9.11 into 10 power minus 31 kg. Speed is given 5.4 into 10 power 6 meter per second. So momentum p equal to mv. We put the value, m is 9.11 into 10 power minus 31 and velocity is given 5.4 into 10 power 6. So we can evaluate it. It comes out to be 4.92 into 10 power minus 24 kg meter per second. Now, suppose we want to find out de Broglie wavelength related to it. So, of course, lambda is given by h upon p. We have got the value of p. H we know, so 6.63 into 10 power minus 34 whole divided by this value 4.92 into 10 power minus 24 kg meter per second. So, this will come out to be 0.135 into 10 power minus 9, which is equal to 0.135 nanometer. Now, for the ball here, second part, Ball of mass 150 gram traveling at a speed of 30 meter per second. Again, same thing we have to do. First of all, we are going to find the momentum, then we will find the de Broglie wavelength related to it. So, mass m dash equal to 0.150 kg, speed is given 30 meter per second, momentum p dash is m dash v dash, that is mass is 0.15 into velocity is 30. So, p dash equal to 4.5 kg meter per second. De Broglie wavelength lambda dash equal to h upon p dash. So h 6.63 into 10 power minus 34 divided by 4.5 into 10 power 4.5. So here mass is 4.5. So after putting the values, lambda dash is 1.47 into 10 power minus 34 meter. It's very small, right? So the de Broglie wavelength of electron is comparable with X-ray wavelength. However, for the ball, it is about 10 power minus 19 times the size of the proton, quite beyond experimental measurement. So that is why when particle nature is there, then wave nature will be almost absent and vice versa. So this is how lesson is over. Now we are going to see the summary, or you can say it is a quick recap. The minimum energy needed by an electron to come out from a metal surface is called the work function of the metal, right? Energy greater than the work function phi 0 required for electron emission from the metal surface can be supplied by suitably heating or applying strong electric field or irradiating it by light of suitable frequency. So these are the methods of electronic emission that we have studied in the beginning of the chapter. Now, second point, photoelectric effect is the phenomena of emission of electrons by metal when illuminated by light of suitable frequency. Certain metals respond to ultraviolet light while others are sensitive even to the visible light. Photoelectric effect involves conversion of light energy into electrical energy. It follows the law of conservation of energy. The photoelectric emission is an instantaneous process and possesses certain special features. Next point is photoelectric current depends on the intensity of incident light, the potential difference applied between the two electrodes, and the nature of the emitter material. Then stopping potential V0 depends on the frequency of incident light, the nature of the emitter material. For a given frequency of incident light, it is independent of its intensity. The stopping potential is directly related to the kinetic energy, and that is EV0 equal to 1 by 2 mv V max square, which is K max. Below a certain frequency, that is called threshold frequency nu 0, characteristic of the metal, no photoelectric emission takes place, no matter how large the intensity may be. What does this mean? It means by increasing the intensity of light, photoelectrons can't be emitted if frequency is below the threshold frequency, right? Then classical picture, the classical wave theory could not explain the main features of photoelectric effect. This is very important point. Its picture of continuous absorption of energy from radiation could not explain the independence of K max on intensity, the existence of nu 0 and the instantaneous nature of the process. Einstein explained these features on the basis of photon pictures of the light. According to this, light is composed of discrete packets of energy called quanta or photons. Each photon carries an energy E equal to h nu and momentum P equal to h upon lambda, which depends on the frequency of incident light and not on its intensity. Photoelectric emission from the metal surface occurs due to absorption of photon by an electron. Einstein's photoelectric equation is in accordance with the energy conservation law as applied to the photon and absorption of by an electron in the metal. The maximum kinetic energy half mv square is equal to the photon energy h nu minus the work function. Of course, energy violation here, energy conservation is done. There is no violation, right? So we can say half mv max square is V0E, that is h nu minus phi 0 or h nu minus nu 0. This photoelectric equation explains all the features of the photoelectric effect. Millikan's first precise measurement confirmed the Einstein photoelectric equation and obtained an accurate value of Planck's constant h. This led to the acceptance of particle or photon description nature of electromagnetic radiation introduced by Einstein. Next point is radiation has dual nature. As we have seen, wave nature and particle nature. The nature of experiment determines whether a wave or a particle description is best suited for the understanding the experimental result. Reasoning that radiation and matter should be symmetrical in nature, Louis Victor de Broglie attributed a wave-like character to material particles. The waves associated with the moving material particles are called matter waves or de Broglie waves. Then the de Broglie wavelength lambda associated with a moving particle is related to its momentum p as lambda equal to h upon p. The dualism of matter is inherent in the de Broglie relation, which contains a wave concept lambda and a particle concept p. Because here m will be involved, here lambda is there. The de Broglie wavelength is independent of the charge and nature of the material particle. It is significantly measurable of the order of the atomic planes spacing in crystals only in case of subatomic particles like electrons, protons, etc. due to smallness of their masses and hence momenta. However, it is indeed very small, quite beyond measurement in case of microscopic objects commonly encountered in daily life. And now here the symbols like Planck constant related to E equal to h nu, stopping potential V0, it is related to kinetic energy, that is V0 equal to k, work function phi 0. So here this is kinetic energy, this is total energy minus work function, then threshold frequency, certain frequency, this is related by formula nu 0 equal to phi 0 divided by h, where phi 0 is work function, and the de Broglie wavelength lambda, it is related by lambda equal to h upon p, where p is momentum. Now we are going to see some more points. Free electrons in a metal are free in the sense that they move inside the metal in a constant potential. This is only an approximation. They are not free to move out of the metal. They need additional energy to get out of the metal. Then comes free electrons in a metal do not all have the same energy like molecules in a gas jar. The electrons have a certain energy distribution at a given temperature. This distribution is different from the usual Maxwell's distribution that you have learned in the study of kinetic theory of gases. You will learn about it in later courses, but the difference has to be with the fact that electrons obey Pauli's exclusion principle. I think you have studied it in chemistry. Now, because of the energy distribution of free electrons in a metal, the energy required by an electron to come out of the metal is different for different electrons. Electrons with higher energy require less additional energy to come out of the metal than those with lower energy. Work function is the least energy required by an electron to come out of the metal. Then observations on photoelectric effect imply that in the event of matter-like interaction, absorption of energy take place in discrete unit of h nu. This is not quite the same as saying that light consists of particles each of energy h nu. Observation on the stopping potential, its independence of intensity and dependence on frequency are the crucial discriminator between the wave picture and the photon picture of the photoelectric effect. And the wavelength of a matter wave given by lambda equal to h upon p has physical significance. Its a phase velocity Vp has no physical significance. However, the group velocity of the matter wave is physically meaningful and equals the velocity of the particle. So this is all about the topic. Now in next video we will study the numericals. Thank you for watching. Team Educate.